Well, hello friends. Welcome back to the JavaScript engine videos. Today we're going to work a little bit on garbage collection. So I'm going to make it so that stack variables in C++ are protected from garbage collection. And here we're just running a very small little test program, right? It just creates a little string and then prints out the fourth character at index 3. And nothing bad happens when we run this program because the garbage collector doesn't really run that often. It only runs on exit. But what if we go and change the allocate function so that when we allocate anything from the GC heap, we'll first do a garbage collection. Now, this is very aggressive, right? And you wouldn't do this, obviously, in a production system, but this can be a pretty good way to sort of flush out problems with your garbage collector. So let me just set up a build. Okay, so now if we run the same program, it will garbage collect anytime that the engine tries to allocate anything. And it's very likely that that will cause trouble. Here we go. So we can see that we crash in below allocate cell, collect garbage, and then we try to mark live cells and something is all wrong. We have some null putter value, something. So let's see what the most obvious fixes here are going to be, and then because I bet you that there's going to be some silly stuff. Mark live cells, and then we can get to the real thing. So let's see. Mark live cells will visit everything that we believe is a root, and the roots are gathered from here, and I guess these are probably null on startup, so we'll just do this for now. And then we don't pass them to the garbage collector as roots if they are null, because null can't be a root clearly. So, alright. What do we have now? So this is sort of more like the thing I was expecting to see. So now we are crashing in the interpreter constructor where we're creating a global object and we're instantiating the console object. So if we're looking at global object, first thing he does is he tries to create a console property on the global object and put a new console object in there. Console object. And this call here to heap allocate is going to cause a garbage collection and things will fall apart. And why do things fall apart? Well, it's probably because of right here. We are sweeping the console object while actually it's not this call to allocate, so this one probably succeeded, but rather we are in here. This call right here. Yeah, put native function. This one causes another allocation of some type, which triggers the garbage collector, and the console object is swept. And so this is the big problem, right? So we have something that we're right in the middle of creating it in C++, and then the garbage collector comes in and says, ooh, well, I'm not sure what this thing is here. I'm going to assume that's garbage, and that's not good for us. So we want to protect this, but we haven't stored it anywhere yet. Like, we don't store it in any variables, or it's not stored in any properties because it's in the middle of being constructed. And in fact, the only place that you can find a reference to this object at the moment is on the program stack. So what we're going to have to do, or program stack or in one of the CPU registers. So what we're going to have to do is figure out everything that's currently pointed to by the stack or by registers, and add those to the set of roots that we consider when we mark everything for liveness in the garbage collector. So what we're going to do is we're going to go here when we gather roots. We're going to also do a conservative root gathering pass. So we'll call that gather conservative roots and make a separate function for that. So this one is his responsibility is going to be to find every pointer on the stack and every pointer in a CPU register and add those to the set of roots that we're already considering. So we'll just make something like this. Okay, and I guess I should add that function here as well so that we have, so the Qt Creator is not so whiny. Okay, so CPU registers is pretty easy. I guess we'll start with that. So we'll make something like a hash table of flatputter. Flatputter is a type def in the system that's either 64-bit int or a 32-bit int, depending on the size of void star. So it's kind of like uint_t, except it's guaranteed to be either this or this. So just showing you what flatputter is. So we'll make a hash table of flatputters. This is going to be our candidate pointers, or like possible pointers, maybe. And now comes the collection phase, right? Or not collection, gathering. So we start with the CPU registers, and there are a couple of different ways that you can find all the CPU registers. You can do inline assembly to copy them out. You can do like a push all registers instruction, or you can do something very simple and just use setjump. So you can make a, what's it called? Jump buff, I think. Setjump. So because of the way setjump and long jump is implemented, basically it's just copying all of the register state into a one of these buffers here. So if you ever look behind the scenes of setjump and long jump, this is probably what you'll find, something like this. And then what we need to do is call setjump. So if you look at setjump, I think maybe it's implemented as assembly, actually, if I recall correctly. Setjump yeah. So it's just this assembly code, and basically it just copies the register state into this data structure. So right now, exactly what we need. And then we can just go through these registers. So from 0 to I guess from 0 to size of the registers divided by size of flatputter, because that's our register width, presumably. Okay, and then possible pointers, then we just add this one. So buff regs I. Okay, and I guess we can start with these, and then we'll do the stack later, because the stack gets a bit more complicated. So say that we just have the registers. So if we print these out now, possible pointer, we'll do something like this. Just so we can see what they look like. Oh, forgot about that one. It'll be interesting to see what our registers look like, actually. So it's still going to crash, but we should be able to see what's in the registers. Right, so these are our registers. And we can see that the console object that gets erroneously destroyed, it's actually not one of these pointers, so it's not in the registers, it's probably on the stack then. So we're gonna have to push forward with this, but I'm gonna do this stack last, I think, because yeah. So the next step, of course, is these are just possible pointers. We don't really know what these are. These are just random values in the CPU registers at this point in time. And I guess we should actually take that here, or yeah, that's okay. So now we got to figure out if any of these are actually like valid garbage collector heap pointers. So what we're going to have to do is we're going to have to go through them one by one and figure out if they point at a heap cell. So we'll do something like possible heap block, or no, even better, cell is cell from possible pointer, and we'll put that in a helper. And then if it is indeed a cell, then roots set cell. Okay, now we just need to implement this thing and we'll be good. So how is this going to work? Well, we have to look at the way that cells are allocated in the garbage collector here is that everything comes out of this thing called heap block, and heap block is allocated on a 16 kilobyte boundary because we align the allocation, which means that we can actually find the heap block for any cell pointer. We can find a pointer to the heap block that's allocated by simply masking off the bottom bits, and that's exactly what this guy here does. So if we just have a cell pointer, even if it's not exactly a cell pointer, like even if it's pointing like into a cell a little bit at an offset, it will still find the heap block because it's just going to remove the bottom bits in the pointer and set them all to 0. So here we'll do possible heap block is heap block from cell, and then we'll just kind of brazenly cast the pointer to a cell here. I think with a reinterpret cast maybe for an extra good boy point. And then we don't know now if this pointer is valid or what. So the way that we validate the pointer is, the best thing we can do right now is to just go through our list of heap blocks, because the heap has all of the heap blocks are in a vector here. So we can just loop through the vector, and we can probably even do this in some other way. M blocks find where block putter is equal to the possible heap block. And if that is M blocks end, then return null putter. Okay, so if we don't find it, then we return null, but we did find it. So if we're here, that means that the flat putter here points somewhere inside of a heap block, but we don't know exactly where inside of it. So I guess we can do something like possible heap block cell from cell at address, maybe? Cell at address, and or maybe, what do we call it? Cell from possible pointer. Maybe that's a better, then we're consistent. Okay, so heap block. Cell from possible pointer. And so heap block, the way that it's laid out in memory is that the first couple of bytes are some metadata. So it's a reference to the heap, the cell size in the heap, and the start of the free list, and then comes the storage. And this is where we store all of the cells. So here we need to check if this is a pointer that points before the first cell in the heap block, then it's still not a valid cell pointer. So if pointer less than flat footer and storage, like that, then we can just say null footer. Otherwise, I guess we compute the cell index, which is pointer minus reinterpret cast to flat footer and storage divided by cell size, m cell size. And then we can just return the cell at that index. Okay, I think that's good. Cell from possible pointer. And I think maybe here we can do something like if it's a null pointer, we can just skip right over it. Because there's no point to look for those. Cell from possible pointer, right. So this is looking pretty okay. Let's see that it actually runs. Okay, so it doesn't work, but maybe we should log the ones that we find. We have the question marks here, so we can log something nice if it actually turns into a cell. So maybe for these we can do something like cell. Just like that. And it seems like none of them were actually live. Okay, well, whatever. Let's see. That looks nice. Okay, then I guess we need to look at the stack then. Fine. So to be able to scan the stack, we have to know where exactly in memory is the stack. And I don't think there's a standard way of looking that up. Like every operating system does it a little bit differently. So that means that we can also do it a little bit differently. Basically, what we want to know is where is the stack base and what is the stack size? And I guess like where does the stack start? So in our case, it kind of starts up here somewhere, so we can make like a dummy variable. Maybe we can do something. I don't know exactly where to put it. We'll make a dummy variable up here. So flat footer dummy. And stack stack reference. A reference point is going to be the address of dummy. So the address, first stack address when we entered this function. Okay, and then we need to get these, and we'll call somebody. We'll call the kernel, get stack bounds, stack base, stack size. If that fails, then we will pair And we'll just assert that we didn't get here. And it seems like maybe we need stdio for that one. Alright, so get stack bounds. It's going to be our little syscall that we invent. So we'll go to syscalls. And we'll invent a new syscall here. Then we got to add it to the process class in the kernel. Get stack bounds. And let's see, flapper base, size t, size. Something like that. And process CPP. So this function is going to figure out what's the stack, where is the stack for the current thread, right? That's what it's going to tell you. So I guess we can just look at the stack pointer at when we enter the kernel. We'll just check what was the user space stack pointer at that time, and then find the memory region that the stack is in, and then we just tell you the bounds of that memory region. So it will be something like flat putter stack pointer is the current thread, register them from the stack, ESP. Oh no, wait, the user space, ESP. And then the stack region is the region from virtual address, and the virtual address is the stack pointer. And if we don't have that stack region, then we can just say einval or something, I don't know. I feel like this shouldn't happen, actually. So maybe we'll say assert not reached, because we're not supposed to be allowed in the kernel if we don't have a valid stack stack pointer. Do I have to provide a process pointer maybe? Yeah, okay. And of course we have to validate our outputs. So if not validate right typed stack base, return default. Stack size. Okay, maybe we'll do those first actually. Okay, so now we should be good. So the stack, let's rename these actually to user. I kind of like to call it, use these kind of names because then it's more clear that these are user space pointers. Just to try to keep track of what's what. So stack base is stack region, or wait, range. Excuse me. Range base get. And the stack size is the stack region size. And then we just have to copy these to user space. So copy user stack base, and to the stack size, we just copy the stack size. And finally return 0. Okay, so this syscall will figure out where does the current stack start and end, or rather, where does it start and how big is it? And then just write those values out to these user space pointers. Cool. Okay, let's just add a C wrapper for this so that we can call it. So since we're in C, I guess we gotta call this like uint putter t. It should be fine. And oh, we have to implement it, of course, in libc. Get stack bounds, user stack base, user stack size. Okay, so now we have a syscall that gives us the stack, hopefully, and we can just call it. And so now we want to go from this point here on the stack all the way to the top of the stack. Because the whole stack, the region that we get out, by default is going to be 4 megabytes. And we don't want to scan all that, right? We just want to scan the part of the stack that's actually used, because that's what we care about. So that's why we need this pointer, or some value here that we can take the address of, because we don't care about anything that comes after this on the stack. So anything that happens after this point, we just care about whatever is on the stack when we ended up in the garbage collector. So that's why we go from this address to the top of the stack. And the top of the stack is stack base plus stack size. So flatper stack top is stack base plus stack size. And then we can iterate stack address is stack putter is maybe this is even easier if we do something like flat putter stack no, let's keep it reasonable here. So the stack address should go from the stack reference to the stack top. And stack address can be incremented by the size of a flat putter every time, because the stack is always in steps of like a machine word. So since we're on x86 right now, it's always 4 bytes. On 64-bit, it would be 8 bytes and so on. So now let's see. So then we want to read from this address to get whatever's on the stack there. So our data is maybe, and we treat the address like a pointer. So stack address, dereference that. I should use read interpret cast. Okay, and then if, well, we can just add it to the set of possible pointers actually. So possible pointers set data. Okay, well, let's do the trick. So here's our dummy, just to have some reference point, and then we get the stack bounds, and then the stack reference point is address of dummy, and stack top is base plus size, and we go from the reference to the top. Yeah, I think this is good. We just collect everything in that range as a potential pointer. Of course, now we get a little bit of rebuilding because I touched serenity.h. Shouldn't be so bad. But I think this is pretty good. Let's see if it actually works. It'd be interesting to see what kind of stuff we find on the stack, because we'll see all the possible pointers here. Of course, we don't distinguish between register pointers and stack pointers. It doesn't matter. Okay, this is taking a bit longer than I expected. I guess everybody has to relink with libc, of course, so that takes a fair bit of time. Okay, so look at that. Now we actually survive the whole thing. So we can see here, we got a heck of a lot of garbage collections now, of course. So let's look at the first one. These are all of the potential possible pointers that we find here. So quite many. And it seems like on the very first call to allocate, there are no interesting cell pointers on the stack or in registers. And on the second call, look at that. So this thing right here, presumably found on the stack, is a valid pointer. And it's a pointer to the global object. And because we find that pointer, then we mark it. And that means that it doesn't get swept. So it doesn't get destroyed. Very, very cool, right? So basically, this is how conservative garbage collection works. At least this is my understanding of it. Probably there's probably some more nuance to it, but I'm kind of implementing this based on how it's been explained to me in the past. So it seems to work pretty well. Now, there are probably still issues here, I think, because we are not doing a heap scan, right? We're only scanning the stack and registers. The heap is just too huge to scan like this, because the heap is going to be like megabytes and megabytes, so we can't go looking everywhere on the heap for anything that might be a pointer, because that's going to make the garbage collector super slow. So the stack and the registers, it's kind of reasonable, I think. And then if you want to store a pointer on the heap to a garbage collected object, then you'll need to mark that yourself, basically. So you have to have some kind of marking reference to it. And usually the way that we take care of that, of course, in libjs is that we have this visit children function that you can override if you are a cell. And it's your responsibility in that function to just inform the cell visitor about any garbage collected pointer that you sort of own, that you want to make sure that the garbage collector does not collect. And that's how this pointer here is protected, for example. So if we don't inform the garbage collector when we are visited here that this needs to be protected, then it's going to get destroyed probably. And I think this is a pretty good scheme. It's a reasonable trade-off, because you can't go scanning the heap. It's just not. There's too slow. So the reason I mention this is because I'm sure that we have JavaScript values or pointers on the heap somewhere that I'm just not thinking of right now. And we'll have to find those and fix those. But actually probably in vectors, because we pass around stuff in vectors. So for example, when we call like a native function, so let's just make a little test program, right? So what we call console.log foo, actually, just like that. I feel like this should probably crash. It didn't. Okay, well that's good. What's something that would crash then? Foo plus bar. No, these are all fine. All right, well, maybe I'm overly pessimistic here. Let's just try random programs. Okay, here's something. So, has on property fails. So what this test does is it just logs whether has on property length is true on I guess what's essentially a synthesized string object. So it's going to be false. But we are asserting here that something has a reference count. And we are in native function call. So we are here, and we are calling, or we're calling a native function callback, which I guess is the hasOwn property, probably. HasOwn property. Where is hasOwn property? Yeah, so here you can see that we have a vector of value. So this is not going to work because vector will store these values on the heap, and then the garbage collector doesn't know to look there for conservative roots. So that's something that we're going to have to fix, but I'm not going to get into that one right now, I think, because we'll just grow the scope of the video so much. But I think the problem here is that when we call toString, then toString, does this allocate? Yes, this will allocate here. Wait, no, it does not allocate. What am I saying? It just, I guess the problem is that the string is already destroyed. Yeah, right. So we have a string object, but it's been destroyed by the previous garbage collection. And we are still trying to do something with it. We are trying to use it somehow, and I guess it's the length string here that's inside of this vector of arguments to hasOwn property. And it was destroyed at some point. I'm not sure exactly when it was destroyed. I guess in the previous call to allocate, right? Anyways, let's make some commits. So there's a whole bunch of things here, but this is pretty nicely separated actually. So let's see, is this call process, and we can do the libc changes. Okay, so this is just a system call that gives us the stack bounce. Very, very simple. And definitely not perfect. You might want to do something more complex, like maybe you should be able to specify which one of your threads do you want the stack bounce for, because right now it's only doing it for the current thread. Maybe it would be nice if like one thread could ask for the stack of another thread, or I don't know. But anyway, add sys get stack bounce for finding the stack base and size. This will be useful when implementing a conservative garbage collection. Okay, and then what did we change in that function? Right, we're just null checking these. I think we should do that one. Or am I being silly about that? Because we could also just skip over null here, because it's kind of weird. So we could just say like if root, then visit the root. Or if not root, continue. It's also fine. It's actually kind of nicer. Yeah, because then we don't have to do all that gunk in the interpreter here. We can just leave it be. And then in fact, we don't even need to do these either. Or actually, we still need to do these. Yeah. So, what did we do? Well, we don't want to keep this one. I think this one is too aggressive. When we allocate, we don't want to GC every time. That's way too much. But it is a useful debugging mechanism, so maybe there should be a way to turn that on somehow. We'll get to that. I guess we can just commit this in one go here. So libjs, implement basic conservative garbage collection. We now scan the stack and CPU registers for potential pointers into the GC heap and include those as any valid cell pointers in the set of roots. I think I wanted to change something about this, because we have this live bit on cells, and it just tells you if there is something living in a cell. So if it's true, then we know that this particular cell is live. But I guess we can use that to maybe avoid some invalid cells in the heap. So gather the roots, conservative, and here. So if we get a valid cell pointer, we can say if cell is live, then we will mark it. Else debug. I can say that, yeah, something like this, because you can have since the conservative stack scan will just look at all of the register values, it's perfectly possible that something is there that's not actually a pointer. It just looks like a pointer, and it just points at a cell that's actually not live. And so we should probably double check before we consider a cell as a valid root, that we should consider looking at the live bit. So I'm just going to test that that still works. Otherwise, we would risk including non-live cells, which would probably lead to trouble. So, and was it has own property? It works, of course, if you don't garbage collect on every allocation. So we only garbage collect on exit now, and we can see that we actually find some things on the stack here. Even when we GC on exit, it's kind of neat. Although maybe these are just the these are the roots, and maybe they are the same things that we already had. Curious. I feel like maybe we should log something about this so that it's more readable. Gather conservative roots. It should be behind heap debug also. Oh, and this one is called GatherRoots, not CollectRoots. Okay, we're still fixing up this commit. Let's see, like that. And if, boom. I mean, we're still going to see all of this because heap debug is enabled, but it's nice to be able to turn it off if you wanted to. Oh, what's going on? Okay, GatherRoots. Yeah, I just wanted to see this thing right here. All right, so let's just add that, and we can write something maybe. This, this works pretty well, but we'll also need to fix solve marking of things passed to native functions. Since those currently in vector value, and the vector storage is on the heap, not scanned. Okay, that's cool. And let's maybe make a debug option so that you can trigger a GC on every allocation. So on allocate cell, we would say like if should collect on every allocation, collect garbage. And I don't know, bool should collect, maybe this can just be a flag actually, on every allocation. False. Okay, something like that. And then we can, from our little JS program, we can set that up. So we'll add a flag for it. We'll collect on every allocation garbage. And we can GC on every allocation and GC on every allocation. Yeah. And then we'll just set that up here. So interpreter heap set should collect on every allocation, GC on every allocation. Okay. Now that would be very useful, I think. And then just dash capital G, maybe just dash G is fine. If you want to run with this mode, it will make many programs crash, but it will help us debug the garbage collector. Let's try it. So if we just run normally, then it crashes. I was not expecting that. Why do you crash? Uninitialized malloc memory. Okay, what on earth did I do now? Wait. Maybe these things were not even linked correctly. Let's try one more time with everything linked. Okay, yeah, so that works normally, and then if we add -G, then we get our crash. Yeah, and then we can work on that next time or some other time. Or maybe I'll fix it up offline, who knows, but I'm not going to fix it now. Anyway, this was pretty productive, so let's just say JS, loop JS plus JS, add a debug option, JS-G to GC after every allocation. This is very useful for discovering collector bugs. Yeah, so I think that we are gonna end the video here for today. So if you made it this far, then I thank you for watching. And I hope you saw something interesting. Personally, I think this is very interesting. This is one of those things that it always seemed like magic to me about JavaScript and about garbage collectors. Like, how the heck does it actually do this? Like, how does it know if something needs to stay alive or what? And when it was explained to me by JavaScript core people, then I was like, oh, okay. It just made so much sense. And now we've implemented it ourselves, and I hope that it made sense to you too. Anyways, this is how the sausage is made. So thank you for checking that out, and I will see you next time. Bye.